All right, the people standing around, please find a seat. All right. All right, hi everyone. Hello. So I want to talk about question 6 from the midterm, and then we'll maybe talk about the midterm more again. Before I start, so I mentioned in one of the sections on Monday that I kind of unreasonably decided that they should buy a laptop with a GPU, and that they now have to carry both a GPU and a charger for a laptop that goes with the GPU. Someone suggested USB-C. Thank you for the suggestion. I tried it. It did not work, at least kind of with the USB-C one charger that I have. So thank you, though. I want to talk about question 6, and also kind of talk about how to approach kind of the more difficult questions. But before I can talk about how to approach it, I need to actually talk about how to solve it. So here's what the question says. So we need to return the next digit of pi every time, right? So like the first time we call, we need to return 3. And then the second time we call it, we need to return 1, and so on. So in terms of how to approach it, oh, I forgot the microphone. Okay, this one does not work. This one does work. 1. Okay, is it good now? No? Yes? Tell me. Well, I mean, I see the people nodding in the first rows, but that was probably fine for you anyway. Okay, people in the back rows, if you can hear me, say something. I know. Hi. Okay, great. All right, because of course, if you could not hear me, that you would not know that I'm asking, so that would be a problem. Okay, all right. So I want to talk about how to approach question 6 from the midterm. So we need the next digit of pi every time. So when I see it, what I would think, this is kind of the example with the generate a pseudo-random number from lecture, because there as well, you got a new number every time you call the function. So when I approach this question, the first thing I would think is, okay, what kind of structure can I take from that example where we generated a pseudo-random number and use it here? All right. So to remind you, I'll do kind of a simple, silly version of the pseudo-random number thing. So not really random. So I'll name it like next integer or something. And we'll have a current integer, and we'll just say current integer plus equals 1, and we'll return current integer. Right? So then if we set the global variable current integer to whatever, 0, then I can say next integer and print it. And that would be 1, right? Because what's happening is current integer used to be 0, and then I'm calling next int. In next int, I'm saying it used to be 0, now set it to 1, and I'm saying return 1. And then the next time I call it, it's going to be 2. Right? And that will be because when I call it now, current integer is currently 1, and then I'm incrementing it by 1, and then I'm returning the new one, which is 2. And then the next time it would be 3, and so on. So this is the basic structure that we also had in the pseudo-random number generator. The only difference was that the transformation of the current integer wasn't as straightforward, right? It was like a times that plus b mod m or something. But the basic structure is the same. Right. So now what I need here is the next digit of pi. So not like 1, 2, 3, 4, rather like 3, 1, 4, 1, and so on. Right. So the way I set it up, it's almost automatic. Because what do I need? So I need, instead of 1, 2, 3, 4, I need some arbitrary array of digits. Well, if I have the digits, so I'll write them here. That's not exactly what we need, but it's almost that. So that's as far as I remember. So if we have the digits, then if instead of returning current, we return digits pi at current, that's kind of what we need. So the only thing is here we set current plus equals 1. So that means that the very first thing that we'd return would be digits pi at 1. So it would be this guy rather than this guy. But that's easily fixed, right? So we can just say current minus 1. And then the first time it's going to be digits pi 0. And then the second time it's going to be digits pi 1, and so on. What is Discord saying? Do we have a quiz today? I don't know. Yeah, probably not. No, you don't. So okay, you can go study for calculus, I guess. And it's not gonna, like 40 minutes is not gonna make a difference, honestly. So okay, so stay with me. You have a midterm next week in this class as well. So okay. So that's going to give you 314 here because I called it 3 times, and then the next time it's going to be the 1 again. All right. So, and that was kind of one aspect of the problem. And if you look at the marking scheme, we have kind of a set amount of marks for getting to this point. Now, there is the other aspect of how do you actually get the digits of pi, because you can't explicitly write them down. You're given them as math.pi, right? So some people, I mentioned that I believe in one section, but not the other. Some people actually try to run around, to do a run around and to just write down the digits of pi that they remembered, because it said you only need up to 10 digits of pi. The problem then arose that some people wrote the digits down thinking that that's enough, but they wrote them down incorrectly. So they misremembered the sequence of the first 10 digits of pi, which I would not have thought that anyone would even try it. Several people actually did know the first 10 and even more. And then the question arose, how do you mark it? Because like the people tried to get around the requirements of the question. And if you do it and you do it correctly, I would say fair enough. But then if you try to do a run around for the question and then you fail at that, then you should lose some points. In fact, I would argue all of the points, but okay. So anyway, let's say that I don't remember the first 10 digits of pi. How would I do it? Well, there's several ways. One of them has to do with lab 2, but that's not actually the easiest way. So the easiest way I would say is to say, okay, so if you import math.pi is going to be this, okay? So how do you get the digits? Well, if you convert it to a string, then now it's just a bunch, it's really is a bunch of digits. So now you can say, get me the first digit, and that's 3. And then 1 is going to be the dot, so we'll have to deal with that. And then this is this, and so on. Right? So that I would say is the most straightforward thing you can do. And by the way, so you can get, so we'll talk about strings in detail later on, but you can get an individual character in a string this way. Just say, I want 0, I want 1, the same way that you would do it with a list. So what does it mean? It means that instead of doing digits pi, which maybe I don't know the rest, I would do str math.pi. And here I'll say, so current, it would be nicer to rename it, but we already started with this name. So current -1. So the only problem now is we got 3.14 rather than 314. So, okay. If you want a hacky way to deal with this, you could just multiply this by a large number or something. So that would do it, because I just moved the dot further down the string. You can also just say, okay, so when current int is 2, I want to increment it more. So I'll say, so if current int 1 rather, I'll just set it to 2. Right? So sorry, 2, of course. Is it? So I want to say when current int is 2 is the problem, because 2 minus 1 is 1. So I'll just skip to the next one. Right? So if I just made it 2, so that 2 minus 1 is the index 1, which is the dot, I'll just advance it by 1 more point. And now I get my 3141 without a problem, and I can get the next one and the next one and so on. Cool. So one kind of note about this. So why did I say here that you can assume that the function will not be called more than 10 times? So why did I say it anyway? I had to say it. Yeah.
Is it because math.pi is a float?
That's right, exactly. So it's a float. It doesn't actually contain an infinite number of digits, exactly. So So what would happen if you do this kind of hack is you get this many digits. It's more than 10, but it's not that many more than 10. And it couldn't possibly be that you have more than whatever, 17, 18, because this is how much information is actually stored there. Right? So that's a limitation. And to be honest, like I knew that was a limitation, so that's why it's there. At the same time, I did not realize that people could just go around it, and because I said it's not going to be followed more than 10 times, so just write down the digits. Yeah. So if you wanted to actually do as many digits as you want, it's possible, right? So with the tools from lab 3, in principle, it's possible to compute pi to arbitrary precision. So you haven't tried it, in part because it would take a really long time with the math. Well, not that long, but it would take some time. It also would take some more math in order to figure out how to actually store all the digits, because what you were doing is storing them in the float, which, like you said, would create a problem once you run out of precision, once you run out of the space for the digits. So it's possible, it's just like harder. So, okay. So in terms of the problem solving, like this is question 6. It wasn't supposed to be an easy problem. I think part of it is thinking, okay, like, what kind of tools from the course can I use? And I think getting to, oh, this is kind of like generating pseudo-random numbers is possible. So the other aspect of problem solving here would be figuring out how do I get one of the digits. And I think like what I did is like the most straightforward thing, but maybe you wouldn't think about, like, maybe it's kind of difficult to think of. I don't know. It's hard for me to tell in retrospect. When I was designing the question, I was actually thinking, like they did something like that in the lab when they were doing the kind of comparing whether the numbers are the same to within the same number of digits. That's kind of the same thing as extracting a digit, right? And that was the way I thought before I figured this one out. I thought that people would do it, right? So like, how do you extract whatever the nth digit of a number? Well, you can just divide it. So you can just kind of bring up this digit to the front by kind of multiplying and dividing, and then round in order to get at the digit, right? So for example, if you know that the number is between 1 and 10, so that means that the format is like X whatever. Then what do you do to get the first digit? Well, you just round, right? So So 3 is the first digit. What's the second digit? Well, several ways of doing it, but one way is to kill the 3. What I mean, kill the 3, subtract int of X. And now it's not exactly X point blah, blah, blah. It's 0 point blah, blah, blah. You can bring it up by multiplying by 10. And now it's the same thing. So I just do int of that. Make sense? So I started with 3.1459. I subtracted 3. So now it's 0 point something. Multiply by 10. So now it's the same format as before. And now I can truncate it again. Right? So what would I have to do? I would have to kind of say current pi is in it, well, pi kind of is initially math.pi, right? And now what I'll do is I'll just say, so it's global current pi. So it's kind of, I'll do a different function. So now what I'll do is I'll say, okay, so I'll return current digit. So the current digit is just int current pi, right? So it's currently, I'm just truncating whatever is current. So this would be 3 initially. And then I want to transform current pi such that the next time I'll get the 1 from 3.1459. So how do I do it? This way, right? So I'll say current pi is 10 times current pi minus int current pi. Right? It's just this process. So the transformation is I take away the whole part of the x. So in this case, I take away the 3, and then I multiply by 10. So that just moves the decimal digit forward. Make sense? Questions? So that's kind of another way of approaching it. There's multiple ways of doing it. And this is like, it's kind of like a math problem in a way, right? So how to approach it? Well, the same way you'll approach the calculus problems tomorrow. So not well. But yeah, kind of think about, and I think this applies to a lot of the Anxi courses, like think about what could possibly, in what I've seen in this course, what could possibly apply to this. Of course, don't just kind of like write it down on a page without thinking. Usually we don't like that. But usually it's the case that something in the course, like something in the lab, something in a project, something in lecture actually applies to the problem. And then sometimes, especially in the later problems on the midterm, you need to apply a little bit of problem solving as well. Like this wasn't an easy question. I'm not trying to pretend that it was. But of course, like it's Q6 on the midterm. It's not going to be easy usually. So in general, I kind of like this story, so indulge me. There was a discussion on YouTube with a chess grandmaster with Hikaru Nakamura, and he was asked, like, what's the smallest possible amount of information that you would need in order to cheat in chess? Like you're playing on a stage, like what would you need for the person to communicate to you in order to get like a significant advantage? And his answer, I think, was interesting. His answer was like, I just need one bit of information. Like, is there anything interesting in the current position or isn't there? Because if I know that there is something interesting, I'll just go and I'll find it. If I know that there isn't, I'll just do whatever I was gonna do. And that's a significant advantage. And I think it's kind of the same in university exams, except in university exams, you don't need to cheat. You already have this bit of information. Usually it's that, yes, there is something interesting to find in the question, which is you need to find what part of the course is relevant to this question and just use that. So in a way, you kind of get to cheat for free. Most questions, not, I have not checked with Professor Davis whether, but I think it's kind of a useful strategy. And again, of course, like some questions are going to be harder than others, of course. So, okay, so this is this one. So Q7, we'll talk about the relevant content on Friday. So you basically cannot do it yet, and I think some of it you will not be able to do. Everything up until Monday, inclusive of Monday, could potentially appear in the midterm. So we'll see how far we get on Monday, and then like on Monday, I'll possibly adjust the midterm depending on how much I cover and go print the midterms. It takes a while to print. So yeah. Okay. Everything else. So I would say, so this one we talked about. So this one is actually a little bit similar to both what you see in this week's lab in terms of the input, and a little bit similar as well to the idea of keeping track of the state in a global variable. Sorry, not really. This is just a while loop. Sorry. So this one I think should make more sense after you've done the lab. So I don't know if you've done so some of you have done the lab, some of you have not done the lab. This one is not gonna, so dictionaries we will not have covered. This one we talked about, and Q7 we talked about. So you're good to go. So I know that we're all busy anyway until tomorrow. So there's going to be some help sessions on the weekend if people want to make use of those. So just on Zoom. And then I'll also kind of look at all the previous midterms and mark out which questions could appear and which questions could not appear on the midterm. Of course, none of them will likely literally appear on the midterm. It could, but probably not. But I'll mark down whichever ones we definitely just have not covered yet. All right. I do suggest that at this point, people, like, even though, like I told you some of the answers, just sit down with one of the midterms, maybe on Friday, and just do a practice run. You don't want it to be the case that you're writing code for the first time on paper when you sit down on the ESC180 midterm. It's different from writing it on the computer. So you want to practice a little bit just writing on paper, and along the way, you'd also be practicing just writing Python in general. When you're practicing in general, I strongly recommend that you try practicing on paper at once, but really it's key to actually run the code that you're writing and see what are the bugs, try to debug it, because kind of it's very easy to fool yourself into thinking that you got the problem if you don't check it. Maybe you did, maybe you didn't. In fact, if you're not practiced in terms of checking your work, you probably didn't get it right. So really kind of debugging, seeing where the problem is I believe like key to learning to write as well. All right. So that's that. I think there was a question, will we be doc marked for including code that doesn't do anything, but also doesn't make us strong? No, but like don't write stuff that you don't need. If we include a global variable that you don't need, no, like we wouldn't subtract marks for that, but like don't do that. Don't confuse the TAs. They're sometimes easily confused. So okay. As are the professors, and not talking about the students. Okay. So the next thing I want to do is I want to talk about nested loops again. So just kind of repeat what I had said. And then I want to point out that actually you knew about nested loops all along. You maybe hadn't realized that. So again, the kind of nested loop that we saw was something like this. So you want like for letter 1 in S, and then we say for letter 2 in S as well, and we print letter 1 plus letter 2. So that's the example from last time. And what that gets you is all the combinations of letter 1 and letter 2. In this case, letter 1 goes from A to F, and letter 2 goes from A to F as well. And you get like all the possible letter 1s, all the possible letter 2s. So the other way to think about it is you're saying for letter 1 in an S, and then letter one is A, then B, then C. And then when letter one is A, it's fixed. And then you're just thinking, okay, so basically what's going on is you're saying letter one is A. And then you're saying for letter two and S, print this. And then you're saying letter two is B. And then you're saying this. It's one. And then you're saying letter one and C. And then you're again doing this, right? So it's the same. So what we're doing is we're just saying letter one is A, letter one is fixed, and then just go through all the possible letter twos. And then again, letter one is now fixed at B, and now go through all the possible letter twos. And so on. So this process actually has a name. It's not that useful anymore. It used to be kind of more important. So it's called unrolling a loop. So this is kind of, by the way, I'm not going to test you on the terminology. So the idea is instead of doing a for loop, you're like literally writing it out. Like first do letter one equals A, and then letter one equals B, and so on. So I'm using that just kind of for the sake of the explanation. When you're writing code, not in Python, where this is really not relevant, but when you're writing code in C, or like even in assembly sometimes doing things this way is like ever so slightly more efficient. The reason it's ever so slightly more efficient is that here I have to, like, it takes computational time, it takes resources to just keep track of the for loop. It sometimes doesn't take any resources to just say letter one is A, letter one is B, and so on. So it becomes a little bit more efficient if you do it this way. Not relevant in Python at all. Like these days, honestly, not relevant in C either, because if you know about compilers, the compiler will unroll the loop for you if it's needed, and it knows, a modern compiler knows much better than you if you need an unrolled loop. You probably don't. But like sometimes you see, like, you know, like not that long ago, like when I was on PUI, I myself did not do this, but like the person in the cubicle next to me like doing this all the time. And I think he knew what he was doing, although sometimes it's a little bit questionable whether unrolling the loop is like the right thing. Anyway, not relevant to Python. This is just a digression. So does that make sense though, as just an explanation of what's going on with the nested loop? Questions about this? So basically what I'm claiming is that this kind of thing is the same as this kind of thing. And I hope this kind of helps clarify people's thinking about it, because this is like a very straightforward thing. Letter one is fixed, and then you just go through all the possible letter twos. And then you fix letter one to something else, and again, you go through all the possible letter twos, and so on. All right. So I want to also say that actually you already knew about nested loops. And what I mean by that, sorry, can we volume down, please, to 0? So I'm gonna find you if you're talking. Hold you out. Okay. So, okay. So what I mean by you already knew about nested loops is this. So here we have some code. So I could write a function that's like, so I'll name it all possible letter 2, and I'll give it letter 1, and I'll give it S. And here I'll say for letter 2 in S, print letter 1 plus letter 2. And now instead of doing a nested loop, what I can do is I can say for letter 1 in S, all possible letter 2 and just give it letter 1, give it S. So the nested loop is gone. That is doing the same thing, right? So that is going through all the letter 1s, and then this function's job is to print letter 1 plus all the possible letter 2s. So this is also the same as a nested loop. And it kind of also makes sense in the sense that you can think about calling a function as just a way to avoid doing a copy paste, right? So it's as if I'm copy pasting this in here. That's always what the function does. Kind of almost so almost what the function does, right? And of course, if you copy and paste this under for letter 1 and S, that's your nested loop back. Does that make sense? So let's, I think maybe not. So let's do all possible letter 2, and then I'll give it letter 1. So like, let's say Z, and S is going to be ABC. Invalid syntax. Seems okay to me. Line 7, 4 letter 1 in S. Oh. So I'll comment this out so that things are clear. And what happens now is, so this one as well, I'll comment out for a second. So what happens here is I'm giving it Z and I'm giving it ABC. And here it prints Z plus A, and then Z plus B, and then Z plus C, right? So then I'm saying that if I first call all possible letter 2 with A and ABC, it's going to be like AA, AB, AC. And then if I call it with B, it's going to be BA, BB, BC. I'm going to call it with C, it's going to be CA, CB, CC. So the same as a nested loop. Makes sense? So then to reiterate what we had done last time, so it's not just 2 levels that you can do. You can do any number of levels, right? So you can say something like for letter 1 in ABCD, for letter 2 in ABCD, for letter 3 in ABCD. That's just going to print all the possible combinations with this, right? So why is it going to print all the possible combinations? Well, let's take it from the bottom up, right? So here, when I run the highlighted part, letter 1 and letter 2 are fixed. And what's happening is I'm always printing like letter 1 plus letter 2, which is fixed, plus letter 3, which goes from A to B to C to D. And that's what we see here, right? So for example, DD is fixed. So this is like D, this D is letter 1, this D is letter 2. And here you see that letter 3 goes A, B, C, D. Right? So this part should make sense. Because letter 1 and letter 2 are fixed, I'm just running this. And then you can go 1 level up and say, okay, so we understand this. So now if we're looking at this, what's going on? Well, letter 1 is fixed. And then we're saying, try every possible letter 2. And then for every possible letter 2, try every possible letter 3. Right? So if we're just thinking about this, it's going to be like A is just a prefix. Letter 1 is fixed. Let's say it's A. And now it's just a nested loop with two levels, which we hopefully already understand. So it's like letter 2 plus letter 3 is like AA, AB, AC, AD, BA, BB, BC, BD, and so on. Okay. So if you understand that, then it's like one more leap to say, well, now we'll just try every possible letter 1. And we already know that the completion is going to work because that we understood. So that's another way of thinking about it. And I think it's sometimes useful, in fact, often useful to think about those things explicitly. It's also sometimes useful to just have this mental shortcut of, well, like this is how you get all the combinations of all the possibilities. All right. So, okay. So for the last couple minutes, unless there's questions, I want to start a new and difficult, admittedly, topic. And this is storing Python objects in memory. So basically, like we discussed, like any object in Python memory, eventually it is going to be some kind of sequence of bits. So we're just going to delve a little bit deeper into how exactly that happens in Python. So every variable name in Python is connected to an address in memory. And we say an address in the memory table. So the memory table looks like this. So we have an address, and then we have a value at that address. So this is going to be a little bit abstracted from what it actually is in the hardware. You'll get the full story kind of in second year, actually. So basically, addresses in memory, locations in memory are just like the physical locations, kind of, in the hardware where you store the bit patterns that represent the values. So I'm going to use addresses that are a little bit made up. So I'll start with address like 1032, and then the next address is going to be like 1064, and then the next address is going to be 1064 plus 32, so that would be 1096, and so on. So when you say something like x is equal to 3456, what happens is Python says, okay, 3456, the integer, is going to live at some address. Let's say at address 1032. 3456. And then it also needs to know, okay, x means the thing at address 1032. So that's going to go in the variable table. And we say that the variable x is going to be referring to address 1032. So I'm going to consistently use this notation where when I'm talking about addresses, I'm going to write this little at sign because it's like at address. This is not a real thing. This is just a notation that I made up. I just want to differentiate between numbers that are addresses from numbers that are just integers, like, for example, 3456. If you know about this kind of thing, but in a context of a different language than Python, or maybe you think that I'm wrong about Python. No, I'm right about Python. It is a little bit weird, but that's how it is in Python. So when you say X is equal to 3, 4, 5, 6, so two things happen. 3, 4, 5, 6 gets to live at some address. And then with Python keeps track that X refers to that address. So for example, the address 1032. You can find what the actual address is. It's going to be different every time you run, because what Python is going to do is it's literally going to say, I need to store this number 3456. So I just need to find some location in the computer, in the computer memory table where I can store this. And you can find where it lives by using ID of X. And the answer is that this number 3456 lives at this address on my computer. It's going to be different on your computer. It's going to be different if you try it again, possibly. So it's not just integers, right? So similarly, something like hello, you say it. So this is going to be a little bit made up. The addresses are going to be different on different computers, but maybe Python decides that hello lives at address 1096. And then here we'll say S is at 1096. Yeah. I mean, not random at all, in the sense that it's all governed by the laws of physics. So it's definitely going to be something. So usually like it looks for like the first available thing in the list of available things that it has available. Sorry, I can't hear what you're saying because people are being loud. So maybe you can ask me after lecture. I want to make one more point, which is, why am I telling you about this? Why is this useful? So the reason this is useful is because of stuff like this. So give me one more minute, please be quiet. So if I have one list that's like this, and then I say L2 is equal to L1, and then I say L2 at 0 is 42, and then I print L1 and print L2, what's going to happen is I change L1, L2 changes as well. And the reason is L1 and L2 are actually the same list. So it's the same address in memory where that list is stored. So I multiply one and multiply the other. So that's why you need to understand this. More details on Friday. I'll see you. Good luck tomorrow. Bye. All right.